yeah, I guess I'll just, thanks. Yeah, the Beyond Self-Healing paper is about a phenomenon of ozone. And I looked up Beyond Self-Healing to see if I was copying anybody. And there was this like chakra book on Amazon. It's called Beyond. I was, oh, okay. But yeah, so today I'll be talking about yeah, protection without poison, why ozone maximizes in the interior of the atmosphere. Yeah, just a tiny bit more about my background. So I come at this problem as a stratospheric scientist. Interested in the state of the stratosphere, not specifically as a chemist. So I'm gonna, sort of be picking up my own understanding of chemistry as we go, and you'll get a sense of what that looks like. My PhD was on the dynamics of a wind pattern in the tropical stratosphere, known as the quasi-biennial oscillation. For that problem, we used the simplest theoretical models available to explain the QBO and ask basic questions like, why does the QBO have a bottom, so-called buffer zone? We also looked at sensitivity to perturbations, and that's a type of approach that I'll bring to the ozone problem. Some inspiration for this ozone work. So ozone, it's a photochemical problem that brings together radiative transfer and chemistry. And some of the inspiration for the approach we take to radiative transfer comes from some work by Nader Givenchy and Stefan Fuchs-Staller and others who look at how in long-wave radiative transfer, the CO2 forcing can often be, one can gain insight into it, analytical and physical insight, by approximating the distribution of absorption coefficients with simple analytic functions, which then relate the emergent properties of that forcing to these spectroscopic properties. And so this talk will be looking at going from spectroscopy to Earth's ozone layer. All right. Who looked at the sun earlier this week through eclipse glasses? Great. Who saw totality? I did not, unfortunately. Okay, wow, more than half. Okay, did anybody raise your hand if you happen to notice that your eclipse glasses set on them, they have the letters ISO and all these sort of language about direct viewers of the sun. Okay, I see some hands. So yeah, eclipse glasses, the ones that they're supposed to be subject to a standard called ISO 12312-2, filters for direct observation of the sun. And it is so that they block ultraviolet and visible light so that you don't burn your eyes. Okay, so let's talk about protection from ultraviolet light. We can think about protection from ultraviolet light in terms of transmissivity. That's the fraction of radiation that gets through some absorbing medium. In atmospheric science, we often talk about the optical depth, where the transmissivity is equal to e to the minus optical depth, indicated by tau. So eclipse glasses, those ISO 12312-2 standards are essentially a transmissivity standard. They have to filter at least zero, they have to let no more than 0.0032% of light through the eclipse glasses. And so in terms of optical depth, that's a tau of 10. The atmosphere also does a large amount of filtering of certain wavelengths of UV light, which protects our eyes and the molecules in our bodies. One of the absorbers in the atmosphere that does a lot of filtering of ultraviolet light is O2. So a characteristic calculation for the optical depth of O2, okay, so you take a representative absorption coefficient. For example, in the UVC, that's very energetic photons, which are sufficiently energetic to break apart DNA and other biological or organic molecules. A typical absorption coefficient by O2 is 10 to the minus 23 centimeters squared per molecule. A column O2, if you multiply that by a column O2, then you get an optical depth of 35. So that means that our O2 at certain wavelengths is like 3 eclipse glasses blocking UV, and in the process protecting us. But at other wavelengths, O2 basically doesn't absorb much UV at all. So essentially, when O2 is absorbing this UV, it's absorbing it and it's breaking apart the bonds of the O2, photolysis. It's photolizing the O2. And there's the photons that lead to this photolysis must have a sufficient amount of energy to break apart that bond. And so the O2 bonds are quite strong. That means you have to have very high energy with low wavelength photons to do that. And so beyond about 240 nanometers in the UV, for wavelengths longer than that, the photons are not energetic enough to break apart the O2. And so O2 is absorbing not much UV at all. And basically, there's no protection coming from O2. And that's OK, because there are other things in the atmosphere as well. And I'll be talking about that today. And so that absorption by O2, which breaks it apart, it drives chemical reactions in Earth's atmosphere. And I'm going to step through a classic model for some of those chemical reactions that lead to Earth's ozone layer. So when O2 absorbs a photon, it breaks it apart and into two single oxygen atoms. One of those oxygen atoms can then bond with another O2. This combination reaction also requires a third body, which is just another gas molecule indicated by M. And they bond to form ozone. And this is the reaction. This is the main reaction in our atmosphere that forms ozone. Once formed, ozone is a very strong absorber of ultraviolet light. And the absorption of UV photolyzes the ozone, and it breaks it back apart into O2 plus O. And reaction number 2 and reaction number 3 happen in quick succession, where that single oxygen atom is bouncing back and forth from being inside ozone, and then it gets photolized and exists as a single oxygen atom before bonding again with O2 to form ozone. And that bouncing back and forth of that single oxygen atom in the process, the ozone layer is constantly being destroyed and reformed and absorbing a huge amount of ultraviolet light in that effect and providing protection for us at the surface from UV light. Some of you will recognize what I'm doing here. I'm stepping through the reactions that constitute the Chapman cycle. It's the foundational model for the ozone layer. There's a fourth reaction of the Chapman cycle, which is that single oxygen atom can bond with ozone instead to form O2. The Chapman cycle predicts an ozone layer that's in the stratosphere, has a peak number density of ozone, that's molecules per volume, around 30 kilometers. I'll talk more in depth about one of our goals here is to understand why the Chapman cycle predicts a maximum there. Now, ozone has weaker bonds than O2. And so ozone is able to absorb photons and be photolized by them that would not interact very strongly with O2. And so, in fact, the strongest absorption coefficient for ozone is much larger than that for O2. It's 10 to the minus 17. A typical column ozone value is 10 to the 19. And so this ozone optical depth peaks at close to 100, optical depth of 100. So that's 10 eclipse glasses. After the eclipse, and on the Facebook Marketplace, my partner took a bunch of people's old eclipse glasses. And so if anybody wants to look at this, this is a terrible day to look at the sun. If anybody wants to look at the sun through 10 eclipse glasses to see what it's like to have an optical depth of 100, you can talk to me after the talk and I can lend them to you. Not very much light is getting through. It's just 100 E foldings, right? So ozone is providing that protection of a huge amount of UV. Ozone is also poisonous. It is poisonous to our lungs. It's poisonous to plants. And so it's a good thing that ozone provides that protection, but it's also a good thing that there's not much down here. So ground level ozone is a pollutant. Stratospheric ozone is very beneficial. And so so our ozone layer provides protection without poison. All right, so now I'm going to step more quantitatively into how this Chapman cycle produces an interior maximum of ozone. Here are those 4 reactions again. We want to know why the ozone layer is in the middle of the atmosphere. Ozone is kind of special in this way. Most other molecules that we think about as being leading order for atmospheric structure are either well mixed, like CO2, or perhaps they're maximizing near the ground, like water vapor. But ozone has this maximum in the middle, so it's a bit puzzling. Now, it turns out that you can actually algebraically solve the Chapman cycle equations in photochemical equilibrium, and you get an expression for the ozone concentration, the ozone number density, and ozone scales with the photolysis rate of O2. So this is how much UV is available to break apart O2. That is called JO2. That's going to be a very important number here. So you have to remember JO2 is the photolysis rate of O2, which is acting as a source of ozone. That's up in the numerator. In the denominator is JO3. That's the photolysis rate of ozone. That is the absorption of photon. That's how much UV is able to drive absorption by ozone. That's also an important number, so you have to remember that. There's some other reaction rate coefficients. There's the molar fraction of O2. There's another key term, which is the air density, n sub a to the which is raised here to raise to 3/2. And the key vertical structure of the ozone layer comes from JO2 over JO3, and then Na to raise to the square root, and then air density to the 3/2. Okay, so we want to understand how is that leading to an interior maximum. It seems like we have the answer here already, but there's a challenge, which is that this equation is actually mathematically implicit. That is because the amount of UV light, that JO2 and JO3, depends on the ozone overhead. And so in general, JO2 and JO3 are spectral integrals across the absorption coefficient by each species, and also including the amount of UV light available. But the amount of UV light available depends on what has not yet been attenuated by O2 and also ozone aloft. And so this equation is mathematically implicit. It makes it hard to reason about, like why does it produce the structure that we see? Of course, it doesn't provide any fundamental limit to simulating ozone. So chemistry climate models are very adept at simulating the ozone layer with much greater complexity than what I'm showing here. My goal is to really understand why these systems of equations, to distill why they lead to the structure that we see. And so we will be using as reference a numerical solution to the ozone layer. And so it's very straightforward to basically numerically integrate the system. You start with UV flux at the top of the atmosphere. You have absorption coefficients for O2 and for ozone. You can see here what I was talking about earlier, which is that O2 in blue absorbs very strongly up to about a wavelength of 240 nanometers. And then it doesn't absorb much UV at all. And that is because the bonds of O2 are so strong that these photons are not able to break the O2 apart. But ozone absorbs even more strongly, and it absorbs out into what we call this extension window. Okay, so we have UV at the top of the atmosphere. We have the absorption coefficients, and you can integrate this Chapman cycle down step by step, jointly solving for the ozone and for the UV flux. And this is a very straightforward calculation. It leads to an expression for the concentration of ozone, shown here, the Chapman profile. And what you can see is that it predicts the correct altitude. You also solve for the UV fluxes, spectrally resolved. And you can see in that peak absorption by ozone, you have 10 eclipse glasses of attenuation. So this color bar here is going across 10 orders of magnitude. You can see that the Chapman cycle predicts the correct altitude for the ozone maximum. And since this chemical system was proposed by Sidney Chapman back in 1930, it has generally been considered to provide our theory for the interior maximum of ozone. But when one looks at sort of modern atmospheric chemistry textbook treatments of explaining the shape of the ozone layer, an interesting thing happens, which is you see that actually textbooks explain the ozone layer in two different ways. I'm going to refer to the first way, which is much more common in textbooks, as the source-controlled paradigm. So most textbooks explain why ozone maximizes in the interior atmosphere. They say, well, the maximum ozone occurs at the maximum in the ozone source. And that the maximum ozone source, we can think of that as being the product of JO2, the photolysis rate of O2, times O2. So that's the production, that's the breaking apart of O2. Now JO2, that's how much UV light you have, and that decreases monotonically and very quickly towards the surface, here in magenta. O2 increases exponentially towards the surface. And so that source is then argued to have an interior maximum at a sweet spot between the product of these two functions. So this is the most common explanation for why ozone has an interior maximum. Has anybody, raise your hand if you've been taught or if you've read or heard this explanation for why ozone has an interior maximum? Okay, great, lots of hands. I gave a talk not so long ago and almost no one raised their hand. I was like, maybe they weren't taught why ozone has an interior maximum. I wasn't sure. So happy to see that people have been explaining this. This is the more common explanation, but there is actually a second one, which is different but appears in a minority of textbooks. The source-sink competition paradigm. The source-sink competition paradigm essentially takes the full vertical structure from the Chapman system, that JO2 divided by JO3, square root, and then O2. And so it's arguing that the ozone maximum results because the photolysis rate of ozone drops off much more rapidly. The photolysis rate of O2 drops off much more rapidly than that of ozone. And then there's additional weighting by O2, which leads to this interior maximum. So we have these two paradigms for explaining the interior maximum of ozone. One of them has an explicit role played by the absorption of UV by ozone. That is the protection from UV that ozone provides us. And so one of the questions we can think about this question is, does the protection provided by the ozone layer actually exert a leading order control on the shape of the ozone layer? In the source controlled paradigm, it does not. In the source sink competition paradigm, it does. Okay, so here's an outline for the talk. Why does ozone have an interior maximum in the Chapman cycle? What about on Earth, which has more things happening than just the Chapman cycle? And what are the implications of these ideas for how the system responds to perturbations? All right, so as I said, the source sink competition paradigm fully reproduces the vertical structure function that comes from the Chapman cycle. So by definition, it must be able to reproduce what's happening in the Chapman cycle. But that leaves open the question whether there might be some way to simplify it and end up with the source-controlled paradigm also being true. This might be approximately the case, for example, if JO3 was not really changing very much in altitude. So let's have a look at that. First, we can just directly test the source-controlled paradigm using a solution to the Chapman cycle. So here's a profile of ozone from our Chapman cycle solution. And I should say here, this is briefly like stepping back, we're focusing here on a tropical ozone profile with overhead sun driving vigorous photochemistry. And I have distilled the problem to its simplest bone. So I'm considering here an isothermal atmosphere, really just trying to elicit how these radiative functions impart structure. And so the result of that is this ozone profile, which is exactly given by the source sink competition paradigm. What does the ozone source look like? What is the production rate of ozone? It actually is maximizing about 20 kilometers above the maximum in ozone. This is often noted. This is widely known and is often stated in the same textbooks, which say that ozone maximizes at the maximum in its source. But it would seem that there's actually about 3 scale heights of tension to that argument. We're going to dig into this a bit more. So, okay, 3 scale heights is kind of a lot, but might it be the case that somehow the Chapman photochemistry still is drawing these two functions together in some way? Are they somehow linked, even though they're far apart? And we're going to test that by retaining the full chemistry that comes from the Chapman cycle, but simplifying the radiative transfer and considering a gray ozone layer, an optically gray ozone layer. And what I mean by that is that we're going to replace the full measured absorption coefficients by constant functions that are fully overlapping. Now, of course, absorption coefficients are properties of the universe. They're not something that that humans are changing over time or something like that. And so this is a thought experiment to see whether we can elicit the structure of the Chapman cycle as independent from what comes from these spectral absorption coefficients. When we consider that gray ozone layer, something interesting happens, which is that the UV fluxes driving the production, the source, and the sink of ozone become proportional to each other at all altitudes. And you'll remember that in this source sink competition paradigm, they lead to ozone. You take their ratio, JO2 divided by JO3. That's just going to be now a constant that's uniform in height. It's going to be weighted by O2. And so actually, the gray ozone layer has a maximum of ozone at the surface. And it's straightforward to solve explicitly for the structure of that gray ozone layer, where now the ratio of the photolysis rates is simply the ratio of the absorption coefficients. This is telling us a few things. So first, okay, the source of ozone is still high up in the atmosphere at some sweet spot. So it's telling us that in Chapman photochemistry, there's nothing intrinsic that requires the source to be co-located with the peak in ozone itself. They can be actually quite far separated. And that's because Chapman photochemistry also has a sink, which is playing an active role in shaping the ozone profile. There's something else it tells us, which is that in order to understand why Chapman photochemistry has an interior maximum, which it does, we need to have some spectral structure beyond this simple gray world. What is that spectral structure? Well, it needs to perform a very particular function. It needs to make it so that the source of ozone, the photolytic source, decays more quickly than the photolytic sink, because otherwise ozone will just continue to increase towards the surface with that O2 to the 3/2. So we basically need this JO2 divided by JO3 to get smaller and smaller towards the ground. And the way that I think nature does this is nature does not have a gray ozone layer, but rather has an extension window, that extension window I referred to earlier, where ozone is absorbing photons, but O2 is not. And the extension window has the effect of exactly allowing the photolysis rate of ozone to decay less quickly towards the surface. It turns out that if you just formulate this model as a two-band model, then you can actually solve analytically for an ozone profile in Chapman photochemistry, which we show here. You have an interior maximum of ozone. Again, that maximum need not be co-located with the ozone source. The Chapman cycle does not require that, but we've now shown that you can get that interior maximum. And so the interior maximum of ozone is a consequence of this extension band, which is in turn a consequence of the weaker bonds of ozone as compared to O2. And so that's our conclusion for the first section is ozone has an interior maximum in the Chapman cycle because ultimately it's because of that weaker bonds of ozone. All right, now we're going to move on. Why does ozone have an interior maximum on Earth? Okay, so first, the reason that these two questions might have different answers is that the Chapman cycle is only 4 chemical reactions. And of course, there are hundreds of chemical reactions occurring in Earth's atmosphere. And people do a very good job of accounting for these in comprehensive chemistry climate models. And the Chapman cycle has some pretty severe limitations in its representation of the ozone layer. It overestimates ozone by about a factor of 2. This is as compared to a MERA2 ozone profile from the tropics, an atmospheric reanalysis. Now, it could be that the Chapman cycle is overestimating ozone by a factor of 2, but perhaps it's still getting the interior maximum for the correct reason. Of course, you see that it does have predicted an interior maximum at the correct altitude. So that's definitely suggests that it might be getting something right. But it could be also that whatever processes it's missing might change the dynamics qualitatively. And so that's what we're going to explore in this section. And to understand the effects of what is missing, you have to know specifically what is Chapman cycle missing that the real world has. And what is missing, it's not that it overestimates the source, it's that it underestimates the sink of ozone. So the Chapman cycle is missing some very important sinks of ozone. This is well known. The first sink that is missing comes broadly from catalytic cycles, which destroy ozone. This goes back all the way to the 1950s, when it was learned that there are natural catalytic cycles involving HOX, which is produced from water vapor when water vapor is photolyzed, from NOx. There are also anthropogenic perturbations to these catalytic cycles, as many of you know with CFCs. And these missing sinks have been shown to get most of the way there towards explaining the overestimate in the Chapman cycle. The Chapman cycle also omits transport. So far I've talked about a system in photochemical equilibrium, but in reality, of course, the atmosphere can lead to deviations of that photochemical equilibrium by moving air around, so that air brings its ozone with it and is out of photochemical equilibrium. And so what we want to do is ask whether these missing sinks qualitatively change how the ozone maximum forms in the tropical stratosphere. All right, and the way we're going to do that is we're going to still be aiming at distilling the effects of these missing sinks. So as is commonly done, we're going to characterize the catalytic cycles as falling into 3 different classes. A catalytic cycle. So as you remember, let's look at this first class. A catalytic cycle is something where you start with some catalyst, call it Z. It can destroy ozone, forming some intermediate. It can destroy ozone again, and you end up with Z at the end. And so you've destroyed 2 ozone, and you have Z again, and so you can restart the cycle. And so this catalytic cycle can have Z as equal to OH. That's that HOX that can be produced by the photolysis of water vapor. There are also catalytic cycles which destroy 2 atomic oxygens. Those are less important in the regions we're concerned with. And most importantly, there are catalytic cycles that destroy 1 atomic oxygen and 1 ozone. And these are the big ones, okay? The HOX, the NOx, chlorine, that's what CFCs unleash in the stratosphere. And so we have these 3 classes of catalytic cycles. And what we want to do is figure out the minimal way to incorporate them into a conceptual picture for the ozone layer so that we can still ask basic questions about how structure forms. And the way that we're going to do that is we're going to augment the Chapman cycle with 2 reactions, 2 fictitious reactions that represent this broader class of catalytic cycles and transport. In one fictitious reaction, we are turning atomic oxygen into O2 at some rate, which we call kappa O. Okay, this is just a damping of atomic oxygen. Our second fictitious reaction turns ozone into O2 at some generalized reaction rate, kappa O3. This augmented system of 6 reactions, again, has a solution. It's not as pretty as the Chapman cycle solution, but what we want to do is see whether we can first validate this picture, reproduce the observed magnitude and altitude of the ozone maximum, and then seek to understand what's going on with this beast. And in order to do all of that, we have to empirically constrain these damping rates, kappa O and kappa O3, based on what we know about catalytic cycles. So that's what we'll step through here. We have the 3 classes of catalytic cycles. And so what we're basically going to do is populate estimates for these damping rates based on the catalysts which drive these cycles. So for example, chlorine is driving this catalytic cycle of O plus O3. And so the damping of atomic oxygen depends on how much ClO you have in the atmosphere. We make 2 non-trivial decisions here. Firstly, we're going to incorporate also an abstracted representation of transport as a damping timescale of 3 months. We've also explored representing transport as a 1D advection. This is in general a 1-dimensional framework. And I'm not claiming that transport actually acts like a damping in general. It looks closer to a damping in the lower stratosphere where it's going to be more important. We also are going to incorporate the fact that for this reaction which destroys O plus O3, the second reaction that destroys atomic oxygen tends to be the rate limiting step. And so the rate at which ozone is destroyed depends on that rate limiting step of the reaction of ZO plus O. Okay, so we have these expressions for the damping rates. Now we basically need to know what is ClO, what are these reaction rates. We take those from an aeronomy textbook, Brazier and Solomon. We're going to use globally averaged constituent profiles from a chemistry climate model called Socrates. We're mainly interested in the tropics here, and so that's an approximation here that is again consistent with the order of magnitude type arguments here, but it's a caveat that should be noted. We're approximating the global average but we're interested in the tropics. And we end up with profile of damping rates. We can have some independent validation for our damping rate of ozone. That's in blue here. It compares reasonably well to a damping rate that comes from a linear ozone model. This is a full chemistry climate model where they look at the timescale over which ozone relaxes from perturbations. And we think that these should look similar, and they do. So now that we have these damping rates, we can now, as functions of height, we can now solve this beast of an implicit equation integrating from the top downwards, just like we did before for the Chapman cycle. And the result is this damped Chapman cycle curve, which I'm showing here in black. It's not a perfect fit to MERA2, and we wouldn't really expect it to be because there's still so many assumptions that have been made, like isothermal and overhead sun instead of a full diurnal cycle. But we are happy about this because it has strongly mitigated the overestimates of ozone from the undamped formulation of Chapman. That's the sort of classical Chapman, which is in that gray curve. And so we're happy that we've gotten rid of the overestimates, and we still have a reasonable prediction for the altitude at which ozone maximizes. And so now what we want to do is understand why is this damped Chapman cycle producing an interior maximum where it does. And to do that, we can do some scale analysis on this beast of a denominator. And it turns out that there's actually 3 useful limits for understanding what's going on here. In none of these limits do the terms that I've crossed out dominate, and so we don't need to focus on those. In the first limit, this J03O3 term dominates, and that's the Chapman. That actually just returns the Chapman cycle limit that we saw before, and that would be the case if kappa O and kappa O3 are 0. Then you end up with the Chapman cycle. What happens if this term in red dominates? Well, that happens when you have kappa O being very large. That's the damping rate of atomic oxygen. Then you end up in an O-damped limit, and ozone will scale like this. It depends on JO2 divided by JO3. There's a factor here of air density cubed. It in general depends different, it has a different functional form than the Chapman cycle, but there's actually some very key similarities between these 2 formulations. In both of them, ozone scales as the source divided by sink raised to some power n times the air density raised to the power 3n. And that means that these 2 formulations actually predict an interior maximum of ozone at the same altitude. For that reason, and because they both have JO3 appearing in the denominator, we're going to link these together in something called the photolytic sink regime. Photolytic sink, that's because JO3 is actively, that absorption of photons by ozone is actively shaping the structure of the ozone layer. And the photolytic sink regime is exactly explained in the source sink competition paradigm. So those textbooks which were explaining ozone using that paradigm could apply in the Chapman cycle, and they would also apply in this O-damped limit, which perhaps maybe more resembles reality, but we're going to have to check. Okay, there's a third limit, which is if this term related to the damping of ozone dominates. Now, if the damping of ozone dominates, then you end up in an ozone damped regime. And ozone scales simply as its source, JO2O2, its source divided by the damping rate. This is familiar for any type of dynamical system which has some driver and has some strong damping. This actually, it has no dependence on JO3 and is exactly the source-controlled paradigm. So if we were in a world with very strong damping of ozone, then those textbooks which explained ozone in terms of maximizing at its source, they might actually be correct. Okay, we're going to call this the non-photolytic sink regime because JO3 is not appearing here. It doesn't, at leading order, the absorption of photons by ozone is not affecting the shape of the ozone layer. All right, so now it's back to an empirical question. We've identified these 2 regimes. Which regime is our Earth in? Well, we can just look at the magnitudes of these terms in our solution. You see that, okay, the Chapman is always small. It's never dominant. That's consistent with general thinking. We see that the O-damped term, the red term, is dominant above about 30 kilometers. Below 30 kilometers, it's the ozone damped term, which is dominant. And so it seems that our atmosphere is in both it's in a photolytic sink regime above 30 kilometers and then transitioning to a non-photolytic sink regime below. And this has implications for how we think about the formation of the ozone layer. So I'm going to progressively step through what I consider to be the most important plot of the talk. Okay, we're going to start by looking at our assimilated ozone profile from MERA2. This is on a log scale. You see the interior maximum. Okay, here's our damped Chapman model, which is producing reasonably the correct magnitude and altitude for the maximum. Now, what I've stated is that the atmosphere is approximately in a photolytic sink regime above 30 kilometers. And so I can plot the O-damped limit for ozone above 30 kilometers. And you can see that that red curve matches quite well the full damped Chapman solution in this region. Now, below 30 kilometers, the atmosphere is in a non-photolytic sink regime where ozone damping, it's more resembling the ozone damped limit, where ozone should simply scale with its production rate. And that's shown by the blue curve. It's the prediction from that source-controlled paradigm. And you can see that the blue curve is, again, doing a very good job of capturing the full damped Chapman solution. But things get kind of thorny because the maximum of ozone is kind of right at this interface between the two paradigms. And actually, neither of these paradigms is able to explain the interior maximum. So the source sink competition paradigm, what we can do is we can imagine extending this functional form down lower into the atmosphere to see where it wants to predict the maximum in ozone. And the source sink competition paradigm predicts a maximum of ozone which is too low, and which is actually in the non-photolytic sink regime where this scaling would not apply. So the source sink competition paradigm cannot explain the ozone maximum, but neither can the source-controlled paradigm, because if you extend the source-controlled paradigm up, it doesn't do quite as bad a job, but it actually predicts a maximum of ozone up in the photolytic sink regime where it is formally inapplicable. And so now we started with these two textbook explanations for the maximum in ozone, but it seems like neither of them actually can correctly predict the interior maximum of ozone. We offer a new theory, which is you can kind of see where this is headed, but it is precisely the transition from a photolytic sink regime aloft, in which ozone is increasing towards the surface, to a non-photolytic sink regime below, in which ozone is decreasing towards the surface, that leads to that interior maximum in ozone. In cartoon form, we can circle back to, we had the source-controlled paradigm, the source sink. But what I've argued here is, OK, in the source-controlled paradigm, the peak is too high. In the source sink competition paradigm, the peak is too low. But the source-controlled is inapplicable above the transition. The source sink is inapplicable below. And what we have in reality is solutions that have been matched between these two, where it's increasing down towards the transition altitude of about 30 kilometers and then decreasing below. We can think of calling this the photolytic transition paradigm. All right, so that's why ozone maximizes on Earth, has an interior maximum on Earth. Lastly, and somewhat briefly, I'll cover some of the implications of this framework for understanding the response to perturbations. Ultimately, a theory, what we want in a theory is a way of thinking about something that we already independently care about. This could be argued. And so we'll see whether this framework offers a way of thinking about the response to perturbations. To start, I will step through. We do have a solution to the ozone layer for a gray ozone layer that produces an interior maximum of ozone for this reason that I'm arguing, for this photolytic transition paradigm. So I'll show what that derivation looks like, mainly to give you some of the language to be able to then understand arguments about how the system responds to perturbations. OK, so if we want to solve this gray ozone layer, we know that we're starting at the top in an ozone damped regime. We continue, and in the gray limit, that JO2 divided by JO3 is simply the rate is replaced by the ratio of the absorption coefficients. And so we have an explicit expression for ozone in the ozone damped limit. The hard part is we have to know, and I should say I'm considering here for constant values of kappa O and kappa O3. So for constant vertically uniform damping rates allow this explicit solution. OK, now what we want to know is what is the transition altitude? The transition between these regimes is given by a criterion that the damping of ozone is equal to the damping of atomic oxygen. And this is an intrinsic part of the solution. Like this transition has to be solved self-consistently with whatever is happening above and below. And that it turns out that you can match that criterion and get an expression for the transition altitude that is not particularly evocative. The transition altitude, it depends on scale height. There's a Lambert W function, which often arises in radiative transfer. I've simplified the system into having non-dimensional parameters, which account for the strength of ozone damping, the strength of damping of O, and the optical depth of O2. But yeah, this expression is helpful in part as an intermediary because it then allows us to get an explicit expression for the ozone at the transition altitude, which in our regime is also going to be the peak ozone of the whole ozone layer. So this is an analytical prediction for the peak ozone in this gray world, which actually is substantially simpler. It's simpler. It still does have this Lambert function, which I'll note is a monotonically increasing function in its argument. And so whatever's in the numerator is making peak ozone bigger, and whatever's in the denominator is making it smaller. We'll sort of come back to some of the intuition that comes from this peak ozone, but I'll step through the remainder of this full profile. So now below the transition altitude, we'll be in the ozone damp regime. Essentially, if you just match the UV passing through this transition altitude, then you can solve for JO2 as a function of height in this below the transition, and that gives you back the ozone. And so now thinking in terms of this, O damp limit, this transition altitude, and then this ozone damp limit, now we can start to think about sensitivities to perturbations. Okay, the first perturbation, I'll consider three. The first one is what happens if we increase the UV, rescale it uniformly at the top of the atmosphere. This could happen from changes in Earth-Sun distance. This could happen from a solar eclipse. If we do that, then ozone actually, in the O damped limit, ozone at any given altitude does not change because the UV enters in JO2 divided by JO3, and that ratio is actually preserved under a rescaling of UV. However, the extra UV does increase the atomic oxygen, which deepens the photolytic sink regime. It deepens that O damp limit, and so the transition altitude shifts downwards. And so you go, and peak ozone therefore will increase because you go farther out on this O damp limit. You now have also additional UV making it into the source-controlled paradigm, and down in the source-controlled paradigm, more UV means more ozone, and so you increase ozone down there. So that's sort of conceptually how the system might be thought to respond with using some thoughts from the Gray model. We can validate that using our full spectral Chapman solution with generalized catalytic cycles and transport. And you can see that there's very little change of ozone in the photolytic sink regime, and then an increase in the peak ozone and an increase of ozone down in the non-photolytic sink regime. All right, secondly, what about the response to an increase in the damping of ozone? This has come from a strengthening of upwelling, an increase of Hawks. If we increase the damping rate of ozone, now we're going to deepen the non-photolytic sink regime upwards because we have more vigorous O damping compared to the more vigorous damping of ozone compared to O. And so by shifting ZT upwards, peak ozone is going to decrease. We're also now damping ozone more vigorously down here, and so ozone will also decrease in the non-photolytic sink regime. We can check this in our full calculation by increasing the damping associated with transport, and you can see that you get exactly that. You get almost no change in the photolytic sink regime, and then a reduction down in the non-photolytic sink regime. Okay, the third perturbation, and the one that is most interesting, is a response to an increase in the damping of atomic oxygen. This is, for example, what happens when you increase CFCs, or when you have nitrous oxide coming from agriculture, NOx from planes flying in the stratosphere. What does this solution tell us happens when you increase the damping of atomic oxygen? Well, that damping rate is appearing in the denominator here, so we're going to decrease ozone in the photolytic sink regime. This increases how much ultraviolet light is making it down to the bottom of the photolytic sink regime, and will actually deepen the photolytic sink regime because more ultraviolet light means that there's more atomic oxygen to be damped. So ZT is going to shift downwards. And what the Gray model predicts something counterintuitive, which is actually that ZT shifts downwards so far that you pick up some of that air density cube term and your peak ozone increases. Your column ozone does not increase, but your peak ozone actually increases in response to this more vigorous damping of atomic oxygen. This is quite surprising. We also have because our column ozone has decreased, we have more ozone down in the non-photolytic sink regime, which simply scales with how much UV is making it down there. Okay, so that is a counterintuitive result. Our fully spectral model does vindicate this. You have the reduction aloft. You have actually a little increase in peak ozone and then reductions down below. It's not just our model that does this. So here's the change in ozone in percentage from doubling NO2 in our toy model. Here's a change in ozone in response to an increase in NOx in a full comprehensive climate model. So if you increase N2O, then you get the reductions aloft, but you're actually getting these increases down with that transition happening right near the peak of ozone, as we predict. Potentially, there's an increase in peak ozone here. It depends on where this model exactly puts the peak. But definitely these strong increases with a transition right in the vicinity of the peak ozone. And this is seen across a whole host of chemistry climate models. I mean, I think has perhaps the way that this has been previously explained is in terms of some chemical reactions, buffering reactions that are happening in this region. But I think these buffering reactions are not strictly necessary to explain why ozone is increasing down here. This model, our toy model does not have any buffering, but it still produces it. So this buffering might be happening in reality, but it's not necessary to explain this overall structure. All right, so that concludes the implications. I think that this work offers a conceptual framework for thinking about how ozone responds to perturbations. Again, I'm not going to spend too much time. This work fits into a broader picture I'm trying to build of thinking about the ozone layer, both in the photolytic sink regime. That's where that beyond self-healing work on the chakras fits in. In the non-photolytic sink regime, we've also thought about how changes in tropopause height can affect ozone down there, where transport is important. And so I'm thinking about these various questions, and I'm always eager to talk about them. I'll go back to conclusions and be happy to take questions. Yeah.
But then doesn't this predict that CFCs should increase ozone somewhere? And is that really?
Yes, so CFCs do. Yeah, let's see if let me pull up. Okay, so here's a full chemistry climate model where they imposed CFCs at 2014 levels on a pre-industrial atmosphere. And you see that term self-healing refers to increases of ozone in response to a chemical perturbation, which should strictly on its own reduce ozone. And so models do predict self-healing. It's not a huge effect, but it's quite robust. It's been noted since the 80s.
So, I mean, should we think of this model as some of the assumptions are clearly not relevant to the poles or something?
Yeah, I think this reasoning, things get very different over the extratropics, where ozone is not. We can use some of the same language. We can say, okay, we have so little UV that we're not in that photolytic sink regime. We're more in a transport dominated regime where ozone is being moved around. The transport looks nothing like a damping. It really, ozone in some limits is going to be basically materially conserved. And so yes, this framework is for the tropics. Back to my conclusions. Yes.
That you're not necessarily atmospheric. I start thinking about this question too.
Yeah. Yeah, it's I think my interest in the stratosphere is what brought me here. Ozone is why temperature increases with height in the stratosphere. Of course, we would still have a stratified layer above our convective layer, but ozone is leading order in shaping the stratosphere. And so I wanted to understand it better. Yes.
It's a great talk. So in the first part of your talk, you said this extension layer like this extension beyond just the gray overlap regime is important for the internal maximum. But maybe I missed it. But in the later part, you don't include that extension.
Right. Yeah. So you have, yeah. What you have noted is that that's exactly right. So to produce an interior maximum in the Chapman cycle, the Chapman cycle atmosphere is fully in the photolytic sink regime. And so in a gray world, ozone will increase all the way down to the ground. You need spectral structure to produce an interior maximum. But that interior maximum is then, it's the maximum which comes within the photolytic sink regime, which is for a different reason than Earth's interior maximum in ozone. And so it turns out you do not need that spectral structure to reproduce the mechanism by which Earth seems to be producing its maximum of ozone in the tropical stratosphere. You do have both. Yeah, so these sort of, whoops. So the gray solution does not have it, but then when I was looking at the sensitivity to perturbations, that was, of course, with the full spectral, which not just the 2 bands, but 150 wavelength bands. And so the system suggests that it's producing a maximum for that same reason, but it can have internal dynamics within the photolytic sink regime that the gray model does not exhibit. Yeah.
I was curiously, so you talk about changes in the atmosphere, being able to change the profile of like. I guess, are there long-term changes in that over its history? You think like volume for the cycle, like you expect that to make a difference, like you create like a long-term history of the profile that way?
There certainly should be, yeah, long-term variability in UV. UV variability can affect ozone, both in terms of the amount of UV, which is that, example I gave was imagining like a uniform rescaling of the UV. There's also important changes in UV which have a spectral character, like the solar cycle has changes in the amount of UV in particular wavelengths. And actually this framework can help us think about that, because sometimes the changes in UV during the solar cycle are changes in the overlap window, and sometimes they're in the extension window. And so changes in the extension window, we would say, well, that shouldn't necessarily affect ozone in the non-photolytic sink regime. Changes in whereas those changes in the extension window should affect ozone above its maximum in the photolytic sink regime. Yeah, I'm not specifically familiar with paleo reconstructions of ozone, so I can't answer your question with any empirical richness. But it's exactly the type of interesting question that it's fun to think about. Yeah.
Using this like should you put this in like a simple simple ozone parameterizations, like intermediate between prescribed and then these linear schemes or something?
Perhaps.
Yeah, like you put this.
Yeah, I'm definitely thinking about putting some simplified representation of ozone in a bigger model as a sort of playground. And yeah, I'm not sure exactly what would be a way to formulate it that tells us something that we didn't already know, right? But yeah, it is something I'm interested in.
Thank Aaron for a great talk. Aaron's around for the rest of the day, and I think he has some meetings in his schedule, but if you need to talk, definitely reach out to me or Sam.
Thank you.